Hi, I'm Jim Doti.
And I'm Christina Dodge.
And welcome to Dialogue. What about that music? Kind of neat mood music, huh? I'm in the mood.
Beautiful. I am too. I just need a glass of wine and I'm set for the day.
Me too.
Really
and
gorgeous.
The music, the violin, was performed by Jack Liebeck, internationally acclaimed violinist, and we'll tell you in a few minutes why he's here. But we also have Brian Foster, university professor of physics, experimental physics, and great to have you both on the show.
Thank you.
Thank you also for the wonderful lecture that you gave right here we're in Memorial Hall, the Memorial Hall stage, on, of all things,
so it's extremely
the theory of relativity, the theory of special relativity, basically Einsteinian physics. And thank you, Brian, for a wonderful explanation of that. And thank you for your accompaniment, Jack. Tell us, what's the connection between physics and the violin, if you will?
Well, I don't know if there's such a great similarity between the actual sort of mechanics of the two things, but I think that many physicists and scientists enjoy playing music as a sort of distraction from their art of trying to sort of work out what's going on in the world. And in some ways I think it helps them sort of diverts their mind away from what they were doing and then come back to their problems. But don't you think that
there's something to the mathematical nature of music and the mathematical nature of understanding physics and science?
Absolutely, there is. I mean, the whole thing about playing music and looking at the notes on the page and decoding them, because they are just a sort of a series of codes and patterns on the page, that definitely is something that is similar. And, you know, the music of great composers like Bach and Mozart and people like that, it's possible to sort of analyze them mathematically in some ways and find out what's going on. I think that it's probably more of a link with scientists looking at music in that way rather than musicians looking at music. You know, we don't necessarily look at it in the kind of the mechanical way as such, but there's definitely a sort of interest. I think it uses similar processes to sort of decoding.
So you're saying that it would be easier for Brian as a physicist to be a physicist and then think about violin as a pastime or a way to relieve his mind or relax.
Kind of like meditation.
In contrast to you as a violinist turning to physics to relax.
Well, I think there are. I mean, I'm very interested in science and physics, and it is my pastime, but I think there's less. If you go to a conference of physicists, you'll find that a vast number of them play classical music or other music on the side as their hobby. I think if you were to go to a symphony orchestra and ask them how many of you read popular science books, and so there'll be one or two hands would go up. It's definitely a different ratio, wouldn't you say, Brian?
Yes.
So are we using our right brain with the music reading and the left with physics, or are they some of both? Or, you know, when you do that, is it like meditation? So you're being able to meditate and then you can go back to the very analytical?
I think that's the way in which Einstein found music helpful to him when he was thinking of his theories. He surely did not somehow think about music and then entwine it in the way he thought about the world. It was the other way around. He would be thinking about his equations to try to describe how the planets move around the sun. And when he got stuck, he would go into his study and take up his violin and play a few tunes. And surely that exercise, a different part of the brain, as you say, somehow would allow a different insight into the problem he was looking at. And then he would be able to go back, put his violin down, and attack the problem with a different insight. And I think that's the way in which music and science really complement each other. They're different activities, but both are intellectually very stimulating.
And maybe they allowed that part of the analytical brain to rest for a moment.
Yeah, I think that's true. I think that's I think that's what people believe actually does happen. And certainly when I'm playing the violin, he would tell me too much. He's my teacher, and he tells me I play too much for enjoyment and not enough for practice. But when I'm practicing, I often, my mind is not at all thinking about the music or thinking about anything else. It's sort of more or less in neutral, and it's a very relaxing experience.
Not the way to practice.
Well, you know, last night,
engage the brain.
Last night you mentioned that Einstein's wife mentioned that he would come out of his office where he's solving equations and coming up with ideas like the theory of relativity, go and play the violin, then go back and then take notes. And the question I had was, when I heard that, do you think while he's playing the violin, he's actually thinking about these equations and not thinking about the music, or is he just relaxing, and that part of relaxing helps him to think more creatively? And I thought of that because when I'm a terrible piano player, but I find it relaxing.
Yes.
But only relaxing in the sense that when I play the piano, I have to really concentrate on the music. There's no way I would be able to think about an economic theory. I'm in the world of music,
Yes.
not in the world of economics.
Yes.
But was Einstein able to?
Well, that's a very good question, and I don't think anyone knows the answer to that, because he was notoriously private about his music. He never let himself be recorded, to the best of my knowledge, so we have no record of how he actually sounded. And I think that was
Maybe
because...
he sounded really awful.
Well, you hear conflicting reports about how good he was. There's the famous story that Piatigorsky said he couldn't count, which, you know, is such a good story that even if it weren't true, someone would have made it up.
Yes,
But of course, he played a lot with the great professional musicians of his time. He loved to play with the great violinists like Kreisler. And they, of course, would have surely thought he wasn't very good. But I think he was probably a good amateur. I think he was probably slightly better violinist than I am, but he was certainly not someone who would have made a living from playing the violin. But going back to your question, I think it's a very interesting one to work out what he was doing, because, of course, he had an exceptional brain. And I agree with you. Yes, I agree with you that when I'm playing the violin, I'm not thinking about physics. But he might have done. It's not impossible for me to believe he might have been thinking about physics at the same time. If he was playing something that he was very familiar with, that he'd more or less memorized, then you can play and think about something else. It's certainly possible.
Well, Brian, you gave a wonderful, captivating lecture last night. It was great to see so many students. And you presented the special theory of relativity, the general theory of relativity, wave theory, which is where Einstein actually won his Nobel Prize, atom smashing, all in a very understandable way, but nonetheless it was challenging. And to have the musical interludes, Jack, with you playing, in a way was like experiencing that difference between intense thinking about a science and then the wonderful relaxation that comes from hearing wonderful music. And you played brilliantly. And we have a clip, because I'd like to share that with our viewing audience. You also had last night a very interesting example. Here Einstein, you think of the theory of relativity, but in terms of, as I mentioned earlier, he actually won his Nobel Prize for his path-breaking work on wave theory. And to explain to an audience, as you did last night, how waves make such a significant difference, that is the difference between the wavelength of light versus sound, and how the size of those waves will determine whether or not you can hear something versus see something through a body was really illuminating. It was, I think, the first time I really understood this concept of wave theory. So if we could also have another clip of you two guys, you playing the light and then violin in back of you. Let's take that clip, because that's a great example, I think, of where Einstein won his Nobel Prize.
Yep. So what we're going to do, or what Jack is going to do, is to use this source of radiation to actually determine the outline of my body. So I'm the object, and Jack will shine the source of light around me, and as the light appears and disappears, then you'll be able to trace the outline of my body with some degree of accuracy. And the reason that works is that the wavelength of light is much shorter than the size of my body. So now we're going to demonstrate what happens when you go to much longer wavelengths. We've brought with us another source of radiation, this time of sound radiation, a much more sophisticated and expensive source of sound radiation. And what Jack is going to do is to explore the outline of my body by producing sound waves, which are going to move around my body. And no doubt you can tell exactly the outline of my body by listening to the music as it goes backwards and forwards behind me. Of course you can't, and the reason you can't is that the wavelength of the sound is so much larger than my body, it just bends around it and gets to your ear anyway. So you can't explore the dimensions of an object of my size with sound. It has too long a wavelength, it's too insensitive, its resolution is not sufficiently good. To explore my body, you need radiation like light, which has a much shorter wavelength. Unfortunately, to look at the properties and size of the atom, light is much too large, it's got much too poor resolution, and therefore we need to go to a much shorter wavelength, much more energetic particles, and that's why we use radioactive particles and accelerated particles to look at the properties of the atoms.
So why is it, or is it important for the average person to understand these theories?
I don't think it's important in the sense that everyone should, but I think that what we find is that there's an enormous curiosity and interest in the general public about Einstein as a person. He's a modern icon, and virtually everybody has heard of Einstein. But also about these attempts that we're carrying through to try to understand how the universe works. People are incredibly curious about how the universe works, about where we all came from, how the Big Bang occurred, what it means for us. And we regularly get very big audiences, people who are not physicists, they're not even scientists, who are very interested by these basic questions about how the universe began.
Right. And
how
everything about us
work.
is physics, practically, right?
Yep.
Or realistically, and it is said that 2/3 of the GDP is due to quantum physics. So could you explain that?
Yes, it's a very interesting statistic, and although you probably as an economist know better than me, I think it's probably justifiable, and the reason for that, of course, is that our modern lives are so based on electronics, which is silicon, and which was invented in the US. The silicon transistor was invented in the US, what, 60 years ago, I forget precisely. And of course, virtually of our modern life is based on silicon, and a great fraction of our GDP is based upon silicon devices. So that's the sense in which quantum physics is at the basis of all of our economics, and it's a very important reason why governments need to invest in basic science, because that discovery of the transistor was not brought around by an industrial company thinking they should develop an alternative to the valve. It was a set of physicists who were in a corner doing things which they thought were very interesting, pure science, and out of that popped, as we say, the basis of our economy. And a similar story is for the World Wide Web, which was invented in CERN for particle physicists to try to exchange information among each other in 4 different corners of the world, and has developed into another area of science which has completely transformed our lives, and no one could have predicted that. But it was done at CERN for completely different reasons related to pure research. So I think we need always, when we're thinking about science and scientific research, to have a balance between using science to get real things into the marketplace so people can buy them and use them, and also balanced with the ability to actually create completely new devices, which are the things which really will change the paradigm, will be the disruptive technologies.
What is the next paradigm shift, or is it just an add-on of what we already know?
Well, by definition, of course, we don't know. As I said, no one could predict the World Wide Web, and no one predicted the transistor. So that's really the key, is no one can predict it. As a matter of principle, you can't predict it. So what you've got to do is make sure you're funding enough basic research right across the patch, not just physics, biology, chemistry, so that you can be sure that there's enough new ideas coming through from which one day this new paradigm will develop. And I personally have no idea where it will be.
So it sounds like our government. We have to just keep funding what we don't know we need to fund.
That's experimental physics, I guess. You experiment. And well, tell us about that incredible atom smasher in Switzerland. We were going to build one in the United States, in Texas, and I think we started, and it was a multi-billion-dollar project, and we abandoned it.
Yes, indeed. I spent several years of my life working on that, so I speak with some authority on it.
So why was it that the United States abandoned it, and now it's in Europe? Does this say something about the U.S.'s commitment to science? And tell us about this incredible atom smasher.
Yes.
As you say, it has important implications, but why is it in Europe and not the U.S.?
Yes, I think it's a lot to do with the stability of science funding, actually. And the one thing which, as a European, my perspective is, of course, special, and so I say this advisedly. In Europe, science funding is, generally speaking, much more stable than it is in the US. Your budget process is such that from one day to the next, people's budgets can be halved, and it's very difficult. If you're building a long-term machine, the LHC took 25 years from the beginning to the very end. Unless you've got that stability of funding, it's extremely difficult to create these sort of things. The SSC, which I myself worked on for a long time, was a great machine. It was a fantastic machine. But the trouble was that the budget kept increasing, and Congress got very restive, and in the end it was just voted down, and that was the end of it. So you know, these things are difficult to predict. CERN has a treaty organization, and therefore all the countries in Europe are locked into the funding of CERN, and to get out of that you have to give a year's notice and you have to pass it in your parliament, so it's extremely difficult, and that stability allows CERN the freedom to plan ahead and to build something like the Large Hadron Collider. So I think that's the major difference, and
Is
that's
the
why
US a partner? Is it a financial partner? Or how do our scientists get to use it?
That's right. The US is not a member of CERN, but it is an associate member, so it does indeed make a major contribution, and many thousands of American scientists are working there. I personally hope that one day the United States will join CERN, and I think that would be an extraordinarily good step, because particle physics is a completely international subject, and I think the days have gone when we need to worry about regional accelerators, and we should really look to an international scientific future. And I think that CERN is a beautiful example of how many countries can come together to work on a particular item of science.
Could you explain to our viewing audience simply and as quickly as you can, what does this atom smasher do? What is it smashing together?
Yeah, we're taking protons, which are one of the constituents of the nucleus, and we're accelerating to extraordinarily high energies, bending them in enormous superconducting magnetic fields, so they curve around in a circle, and then they meet in various experiments, and when they meet, they give rise to thousands of particles using Einstein's formula: energy equals mass times the velocity of light squared,
E equals MC squared.
To produce these thousands of particles, which then we measure in our detectors, and by looking at the properties of these collisions, we can work out things about how the universe began, and what the smallest particles are and how they behave.
There's something
Wow.
I was thinking about last night, because I know you're more on the experimental side of physics, and we have a great physicist, Yakir Aronov, who
Yes.
just received the National Medal of Science, and he's a theoretical physicist. And as you were explaining atom smashing, it seems to me that you're experimenting without a basic theory that comes before it. I'm an economist, and when I write an article, I'll have a theory and then I test it. Whereas it seems like with this atom smasher, you're smashing particles together and then coming up with findings, incredible findings. But there's no theory to guide you in terms of what you think's going to happen before it happens.
No, that isn't in fact correct. I mean, there are many theories. I think it's not, in a sense, the problem is the reverse. It's not that we don't have theories about what might happen, it's we have far too many, and the purpose of experimentation is to try to narrow them down to one or two candidates which may be able to be further developed. And another thing that you have to be very careful of is that when you're doing these experiments, you don't let yourself be tunneled into looking for a particular thing in a particular way and then miss something subtle which you haven't thought of. So you've got to be as open-minded as you possibly can, and as an experimentalist I strongly believe that we need to take the data, we need to make sure we understand how we've got it, we need to understand its properties, and then the theorists come in and try to fit it to their theories and see which ones work. That's, I think, the only way to do it.
And do you have a list of alternatives that you have to do in the experiments?
Yes, there's a large number of possible theories, and once the data is processed properly and we understand all the properties of the data, they can be tested against the various different theories, and some of those will fail, some of those will not match up with the data.
Are the scientists pleased with the results? I know there were some problems at the beginning, but they're a multi-billion-dollar effort, so you knew that it was there would be a staging problem. But now that it's working, is it everything it was cracked up to be?
You're right to say that there were problems at the beginning. It's a unique machine. There's nothing like it anywhere in the world. It's just an enormous cryogenic device. It operates close to absolute zero, much colder than outer space. And no one has ever run anything like that before. So there were problems, but now it is working extremely well. People are very pleased with how well it's running. It still will need 2 or 3 years of increasing its potential, increasing the number of collisions that we can get, increasing the energy of the collisions. And that's a gradual process which was always intended. So it's on a very nice trajectory, it's working extremely well, and exciting results are already starting to be seen. So
are you playing classical music in the background so that making sure that your intellectual capacity is at its fullest?
Yes. That's your music.
Yes, when people are operating the experiments, many of them listen to headphones, and some of them are surely listen to classical music.
Yeah. No Lady Gaga.
On that note, here, Brian, Jack is your teacher in terms of the violin.
Yes.
Jack, have you picked up any physics along the way?
Oh, yeah.
Is Brian your mentor with respect to learning about experimental physics?
Yeah, absolutely. I mean, well, I wouldn't say that Brian always says you can come up with sort of, I can understand the descriptions he gives, and I can read popular science books and things, but unfortunately my mathematics isn't quite up to the task, so I'm never going to really understand it at a fundamental level, but certainly I picked up a lot of physics, and I mean, it's actually something that as a kid when I was at school I had to do a lot of practice, and I had to really let some of my other subjects sort of put them in the background and just do the bare minimum so that I could get on with my practice. And so in a way, physics, if I wasn't playing the violin, would have taken a lot more seriously. So it's been a brilliant journey for me to I mean, when we're on the road, I can ask the most ridiculous questions and see what the answers are, and really, I've heard the lecture a lot, so I've managed to think of different ways things work, and it's quite funny when we've met up with Nobel laureates all over the world doing these things, and we sit and have a drink with these colleagues of Brian's in the pub afterwards, and I can pose a question which gets them all arguing, and I really enjoy that.
Well, and I can questions which are more perceptive than my graduate students.
Well, the ridiculous questions are the ones that are going to prompt the answer one day, right? The out-of-the-box type thinking. Absolutely. Yes.
Any particular reason or theory that you have that Einstein preferred Bach and Mozart?
Well, I think that well, he was obviously an incredibly intelligent guy and very and opinionated about classical music, the music he loved, and I think he just loved the simplicity and beauty of the music. They are really the sort of the absolute gold standard of classical music. It's pure and simple, and that's really what he appreciated. I think once you start getting into sort of Wagner and things, it's a completely it's classical music, but it's a completely different complexity, and it's in a way for him probably was completely over the top and not pure at all. So I think he just loved that simplicity and purity to it. I mean, the music is so perfect. I mean, as a player, you get the impression when you're playing Mozart and Bach that the only thing you can do with it is ruin it. Because on its own, it's absolutely perfect. It's just amazing.
That's really incredible. Thanks for sharing that with us. That's interesting way to think about truly great music. Congratulations. We're just about out of time, but congratulations on your new film that you did the score for Jane Eyre that will premiere.
I played on the score for this new movie that's coming out. Well, it should be out now, I think. And it's very exciting to be on this. I've always dreamt of working on movies, so I'm very excited.
Did it meet your expectations?
I haven't actually seen it. I've only heard it. So,
okay.
I've seen bits of it as we were recording it, but I think the film looks great, and the music is absolutely beautiful.
And Dame Judi Dench is going to be one of the actresses.
Yeah, absolutely.
It should be wonderful. But thank you for being part of our 150th anniversary.
Great pleasure.
Thank you.